Hi, today we're going to talk about the space-time Pythagorean theorem. In the Euclidean space, we know that the length of the longest side of a right-angled triangle is equal to the sum of squares of the other two. This is called the Pythagorean theorem, which we all know about. But in the kind of space that we are dealing with in the Einstein special theory of relativity, which contains an extra dimension for time in spite of just having the spatial dimensions, the relationship between the side lengths of a right angled triangle is slightly different. So, what is that relation? Without further ado, let's get started. In our universe, there are three spatial dimensions and one time dimension. In the spatial dimensions, you have the freedom to do whatever you want, whereas in the time dimension, you are restricted to move towards the future. So even if an observer is stationary in space, it's not stationary in space-time. That's because it will have to move through the time dimension. Okay, so let's have a look at our coordinate system. So this axis represents the time measured by a stationary observer, and this axis represents the length measured by a stationary observer. And there's a problem with this coordinate system, and that's having two different measuring units for the two axes, and we want both the axes to have the same measuring unit. So we are gonna multiply, we're gonna stretch out the time axis by by a factor of the speed of light to bring this to the same measuring unit of this axis. So we know that the speed of light is the conversion unit between time and space. Time multiplied by the speed of light equals space. So we are going to stretch out this axis by a factor of c, multiply this axis by c, and then we would have a coordinate system that actually works. Consider an observer who's moving at a constant velocity with a light clock. A light clock is a box with two parallel mirrors with a ray of light bouncing back and forward between those two parallel mirrors. From the perspective of the stationary observer, the light ray is going to go from here to here. It's going to take a diagonal path. But from the perspective of the moving observer, the light ray is going to go from here to here. It's going to go straight up. And this observer, the observer who's moving, is experience a shorter time for this process to happen. That's because he's moving both through space and time, and the space-time velocity is distributed through both of the axes, and he's experiencing a shorter time, and he's experiencing a longer time period for this process to happen. So the diagonal path, the length of the diagonal path that light takes from here to here is equal to c, the speed of light, multiplied by the time period measured by the stationary observer. And this length, the distance traveled by this light clock, or else by this moving observer, is equal to the velocity of the observer multiplied by the time measured by the stationary observer for the light ray to go from here to here, and that's Vt, and this length over here is equal to the speed of light multiplied by the time measured by him for in order for the light to travel from here to here, and Tm stands for t moving, and the speed of light is constant. According to Maxwell, the speed of light is constant, and the speed of light is not going to change, and we can use Pythagoras to build up a relation between these three quantities. C squared t squared, which is distance over here, squared, is equal to c squared times t moving squared, which is this length over here squared, plus v squared t squared, which is this length over here squared. And that's good old Pythagoras. It all works right because this is a right angle triangle. So the space-time trajectory taken by the moving observer is going to look something like this. And from his frame of reference, this is going to lie exactly on his time axis, and we have to do the same thing that we did for the stationary observer's time axis. We must stretch everything in the direction of the time axis by a factor of c. So because this lies exactly on the time axis of this observer, we can simplify its magnitude by simply multiplying it by the speed of light. So the time experienced by him is Tm, and we are going to multiply it by c, and then we're going to get the length of this. The length of the space-time trajectory is always equal to the time experienced by the observer. So this is going to equal c times Tm. So as you can see here, this is a right angled triangle, and this is the hypotenuse. The hypotenuse squared is equal to c squared times the time squared minus v squared t squared. Well, what is Vt? Vt is the distance traveled, and that's the same as x squared. And we can also extend this relation up to higher dimensions. If we have 3 dimensions, it's x squared minus y squared minus z squared. At a glance, one might think that z squared is equal to x squared plus y squared, but actually z squared is equal to y squared minus x squared. That's how things work in space-time. In the regular Euclidean space, if we have a right angled triangle with side lengths x, y, and z as shown in this picture, z squared is equal to y squared plus x squared. But that's not the case in space-time. In space-time, the hypotenuse squared is equal to y squared, where y is the length of the side of the right angle triangle that's aligned with the time dimension, subtracted by x squared.